Good morning. So, I am Dr. R. Murugan, Professor in the Department of Mechanical Engineering. Today, we are going to see about design of shaft. Actually, in the design of machine element, the design of shaft is a important and critical component. So, in the session, we are going to see the very brief introduction about this topic, design of shaft. What is a shaft and what are the forces acting on the shaft, and how the stresses are developed inside the shaft, and how the design is made for the shaft member. So, we will briefly go through this one. Actually, shaft is a rotating machine element which used for power transmission purpose. So, in mechanical engineering, any machinery is running under the prime mover. So, to transmit power from any prime mover to the machinery, we have to transfer the power using this shaft. So, the shaft is a rotating member, and over this shaft there are pulleys and gears connected on it. So, if you see the geometry of the shaft, commonly the shaft is a circular cross sectional member. It may be a solid one or a hollow section, depends upon the requirement. Suppose if we want to go for the lightweight design, then they prefer the hollow shaft. Otherwise, the solid shaft is the best suited one. If you take the material used for the shaft design, the material should have very high strength, good machinability, and it should have low notch sensitivity factor, and it should have good heat treatment properties and high wear resistance properties. The commonly used shaft materials are 40 C8, 45 C8, 40 C4 and 50 C12 grades. And these are the stresses acting over the shaft. Already I told you, shaft is a rotating machine member. So, any member which is rotating on its own axis will be mainly subjected to shear stress. So, the shear stress, if you see this diagram, so shaft is subjected to twisting moment because it is a rotating member. So, this twisting moment causes the shear stress. If you see the shear stress distribution, in the outer surface the stress value will be maximum, and the inner surface the value will be 0. So, the shear stress is distributed like this from inner to outer. So, inner is minimum, outer is maximum, and because the various parts like pulleys, gears mounted on the shaft is also subjected to bending stress. So, if you see the bending stress distribution, again in the same pattern, the bending stress at the center or axis of the shaft will be 0, and if you move towards the outer surface of the shaft, the stress value will be maximum. So, when the shaft is subjected to pure torsion or twisting moment, we have to consider this shear stress alone. Suppose if it is subjected to pure bending moment alone, then you will have only bending stress. But if you take any operating condition, any shaft will be subjected to combination of these two, bending moment and the twisting moment. So, it will be subjected to combined torsional and bending stress. So, to design a shaft, first we should know what are the loads acting over the shaft, whether it is subjected to purely twisting moment, purely bending moment, or combination of these two. So, now we will go to the procedure how to design the shaft which is subjected to the different kinds of loads. Now, when you want to design a shaft, first we should know what is the maximum stress we can offer for the material. So, this is prescribed by the standard American Society of Mechanical Engineers. So, according to ASME, we can design a shaft for the maximum level of 60% of the yield strength, that is 0.6 times sigma y, and the shear stress is maximum of 0.3 times sigma y, that is 30% of the yield strength of the material. So, a shaft design, there are 3 methods available. So, we have to design the shaft based on strength as well as rigidity, then in vibration condition, that is design based on the critical speed. Today we will see only the shaft design based on the strength alone. So, as I told you earlier, the shaft may be subjected to different loading condition first one, if it is subjected to twisting moment alone, that means it is has only pure rotation. Second condition, it has purely subjected to bending moment. So, the only transverse load is acting on the shaft. Then the third one, this is the normal operating condition, the shaft will be subjected to combined twisting and bending moments. So, in some cases the shaft may also subjected to axial load in addition to twisting and bending moment, and most of the practical situation these loads will be in the fluctuating type. So, now I will tell you the steps to be followed for each cases. So, now we will take up the first case. If a shaft is subjected to pure twisting moment, that means it is purely rotating, right. In that case, we know that shaft is subjected to only the shear stress, and shear stress distribution is inner layer or in the axis of the shaft the shear stress will be 0, in the outer the shear stress value will be maximum. So, if you want to design a shaft which is subjected to twisting moment, then we have to use the famous equation which we have studied in your solid mechanics, the torsion equation. So, this torsion equation is nothing but T by J is equal to tau by R. Here the T is the external twisting moment acting over the shaft, and J is the geometrical property which is called polar moment of inertia, and tau is the shear strength of the material used for the shaft, and R is the radius of the shaft. So, if you use this equation, then in this slide it is explaining about the shear stress distribution as I told you. So, the inner or axis of the shaft shear stress will be 0, and it is in the outer surface the shear stress value will be maximum. This is for the solid shaft. Suppose if we go for the hollow shaft, to reduce the weight of the shaft, the shear stress distribution will be in this manner. So, in the inner layer the shear stress value will be minimum, outer layer it will be maximum. So, in case if you use the torsion equation for solid shaft, then the polar moment of inertia of the shaft will be equal to pi d power 4 by 32, already we know, and if you substitute this value in the torsion equation, and the radius of the shaft is diameter by 2. So, you will get the final expression for the design of a shaft. This is the final equation we are deriving from the basic torsion equation. So, T is equal to pi by 16 into tau into d power cube. So, in this if you see this equation, in the left hand side we have the load or twisting moment acting on the material, in the right hand side we have strength of the material, and we have the geometrical property d. So, by comparing the load and the strength we are able to design the shaft. Suppose if you want to know what should be the diameter of the shaft, you can substitute the load at, that is twisting moment, on the left hand side, and substitute the strength of the material tau, then you are able to get the diameter required for the shaft. Similarly, it is if it is a hollow shaft, the polar moment of inertia expression will be in terms of outer diameter and the inner diameter. This will be the expression. If you substitute this J value in this torsion equation, finally we end up with this equation, which is T is equal to pi by 16 tau do cube 1 minus k power 4, where this k is called diameter ratio. So, di by do. So, if we choose solid shaft, we have to use that equation. If it is a hollow one, we have to go for this equation. Next case, if the shaft is subjected to pure bending moment, then we have to use the equation, bending equation, m by I is equal to sigma b by y. So, here this m is the external load, that is bending moment acting on the shaft, I is the geometrical property, that is moment of inertia, sigma b is the strength of the material, that is bending strength of the material, and y is the distance from the axis, neutral axis of the shaft to the outer layer, to which we are calculating the stress. Then in the bending moment, again for the solid shaft, we know that the moment of inertia value is pi d power 4 by 64. So, when we substitute this I value in the bending equation, so we will end up with the equation m is equal to pi by 32 sigma b into d power 4. So, again I told you in this equation the left hand side we have the external load, that is bending moment, and the right hand side we have the strength of the material. So, by comparing the load with the strength of the material, we can get the required diameter of the shaft. So, in case of hollow shaft, the equation will be the final equation pi by 32 sigma b do cube 1 minus k power 4. So, here k is the diameter ratio. So, in any practical situation, if you take a shaft which is used in machineries, it will be subjected to both bending moment as well as twisting moment. So, suppose if you have a shaft subjected to combined twisting moment and bending moment, how to design that one? So, in that case the shaft is subjected to both bending stress as well as shear stress. So, when you have combination of stresses acting on the material, so the only option to solve the problem is we have to use any one of the theories of failure. So, the theories of failure compares the stress developed in the material and also strength of the material. So, here the shaft is made of ductile material. So, we are going to use the maximum shear stress theory or maximum normal stress theory. So, when we apply these theories, we will end up with the final diameter of the shaft. So, according to maximum shear stress theory, so we have the expression tau max, that is maximum shear stress possible on the material will be equal to root of sigma square plus 4 tau square. So, as I told you, the sigma and the tau should be measured based on the pure bending moment and twisting moment. The sigma value is nothing but bending stress induced due to bending moment alone, and this tau is nothing but shear stress induced due to the twisting moment alone. So, after calculating these two by using the bending equation and torsion equation, substitute that value. So, we will get the tau max value. So, that tau max value should be used for designing this shaft. So, the I equation is slightly rearranged to get these terms called equivalent twisting moment. So, when we substitute that value of sigma and tau, the equation will become in this format. So, here we have root of m square plus t square, which is called a equivalent twisting moment. So, this equivalent twisting moment is considered as the external load acting on the member. Again, we can compare this external load to this equation pi by 16 tau d cube to get the required diameter of the shaft. So, this diagram will show you what is this shaft. So, this is a central member is the shaft which is supporting the pulleys and gears on it. Actually, the shaft two ends are supported at the bearing, and the shaft is supporting the members which are used for power transmission. So, thank you.